In this lesson we're going to look at magnetic fields. Now, in the area of magnetism, what we mean by a magnetic field is it's the region around the magnet where the magnetic force acts. And this magnetic field can be represented by magnetic field lines as indicated here. So let's just make a note of that. These are the magnetic field lines. These show the direction of the line of the magnetic force. So as you know, we've got the north pole and the south pole of the magnet at either end of the magnet, and what we can say is that the field lines always move from north to south. You can almost treat the magnetic field as if it were a type of river which flows from the north pole through to the south pole. So think of it as something as flowing. Actually, in physics, you might be interested to know that the word given for this field, for these field lines, is flux, which has the same origin as the word fluid or flow. Okay, so the idea of something flowing from north to south pole. Okay, and that helps us understand the direction of the magnetic field. So we can say that the magnetic field has a direction. It always flows away from the north pole. Okay, like that. And it always flows towards the south pole. Now, although these field lines are invisible, we can observe them using a couple of simple experiments. For example, so one thing you can do is you can cover your magnet with a firm sheet of transparent plastic and then sprinkle iron filings on top of the sheet. If you don't have a sheet of plastic, then you could use a piece of paper. What you don't want to happen is that the iron filings come in direct contact with the magnet, because it's a very difficult job to remove them after that. So you can very clearly see the presence of these field lines manifested in the way these iron filings distribute themselves around the magnet. Another way we can demonstrate the field lines, and in particular the direction of the field, is to use little button compasses. So if I position a button compass here, for example, then the needle of the compass, which is also just a little magnet which is able to rotate, will align itself with the direction of the field line, and it will point away from the north pole of the magnet. If I position it here, for example, then at that very point the magnetic field is flowing upwards, and the needle of the compass will align itself in that direction, so it will point upwards. If I position the compass here, the needle will point to the left. If I position it here, it'll point downwards. And if I position it here, it'll point again towards the south pole of the magnet. Okay, so two ways of demonstrating the magnetic field lines: iron filings, or even better, little button compasses, and these actually show you the direction of the field lines. Okay, so what else can we say about our magnetic field? Well, it is actually the magnetic field which produces the force, and where the magnetic field lines are closest together, then the force is greatest. Here, that's to say, where the field lines are closest together, the magnetic field intensity, the intensity of the magnetic field, is greatest, and so the force is greatest. And this always occurs at the poles of the magnet. So the force is greatest at the poles, where the field lines are closest together. And we can also say that the size of the force depends upon the distance from the poles. That's to say, as you move away from the poles, the field lines become more and more separated, so the intensity of the magnetic field is less, and the force produced by the magnet is less. Okay, so summarize that. The further from the poles, the weaker the force. Conversely, the nearer to the poles, the greater the force. Okay, so let's just have a look at how these magnetic fields can interact with each other in simple situations. So, as I just stated, the magnetic forces occur because the magnetic fields interact with each other. So in this case we've got a north and a south pole interacting, and you'll notice that in between the ends of the magnets this will produce a uniform field. That's to say, the field lines are parallel between the north and south poles of the magnet. Okay, so that produces a uniform field distribution. Now, when the poles of the magnets are the same, that's to say you've got a north against a north, or a south pole against a south pole, then you'll notice that the fields produced by the two magnets tend to oppose each other in this way. So you get a repelling force with north-north, south-south. Likewise, you'll also realise that in the centre of this region, exactly in between the two poles, there'll be a point where the two magnetic fields cancel out, and at that point the magnetic force will be zero.